For the next lesson, we're going to look at what happens, what are the special points that we can determine, sometimes using the derivative and sometimes using some other pieces of information. So let's take a function. We are going to draw our lovely function. Okay. We can see a few points that are special here on our function. So we are going to talk about these points in terms of being a maximum or a minimum. And so you've seen maxima and minima before when we're talking about a quadratic function. So a quadratic function has we would talk about this point right here as being a maximum, as particularly the y value is the maximum value. And we would talk with a quadratic function here about the y value being a minimum value. We are now going to expand this and talk about maxima and minima with some more complex function. And in order to do this, we're going to have to get a little bit more specific about what kind of maximum and minimum we're talking about. So we're going to look at this function here that is defined on a closed interval between a and b. So f of x on the closed interval a, b. This point right here is what we call an absolute or global maximum. It is the highest point the function attains on this interval. So it's the highest it can possibly get. Okay. Just like our maximum with the parabola, that was the highest point that function ever got to. So that was an absolute maximum. This point right here is called a relative or local maximum, as is this point right there. So a relative or local maximum, we'll talk about the precise definition, is the maximum for some open interval that's right around that point. Similarly here, we can call this a relative or local minimum. So it's the lowest point around, but it's not necessarily the lowest point on the whole function. This point right here is an absolute minimum. So it's an absolute minimum because it is the lowest point on the function, but it is also a relative minimum because it's also the lowest point around in its area. Notice our first absolute maximum, it is not a local maximum because on the left-hand side, we don't have any more points to compare it to, so we don't know. In order to be a local maximum, you have to have points, you have to be part of an open interval, so that means you need points on both sides. And here we have a point that is neither a maximum or minimum. And it's also not a relative or local. So it's not relative, it's not absolute. It is no kind of maximum and no kind of minimum because it is not higher than all the other points around it, and it is not the highest or lowest point on the whole graph. Okay? So if we go back to looking over here at our quadratics, our maximum and minimum, the maximum for a quadratic, we didn't have to define it as just the relative or just the absolute maximum because it's both. Same here with the minimum, we never had to define an absolute or a relative minimum because it's both. We don't have to worry about it. So we're going to go through the 4 definitions of absolute and relative maximum and minimum. So let's do our maximums first. Okay, so f of x has an absolute maximum at x equals c if f of x is less than or equal to f of c for all C in the domain of F. That is our absolute maximum. So essentially what this is saying is that it's an absolute maximum if all y values are less than or equal to this particular y value. Okay, so it has to be the highest y value that we have on the whole function. Other ones can be equal to it, but they cannot be any bigger. There cannot be any other y values that are higher. So you'd say f of x has a relative maximum at x equals c if f of x is less than or equal to f of c for all c element of a, for all x that are in an interval ab such that, you'll see this abbreviation sometimes, c is also in ab. So there has to be some open interval around our x value, around our point c, so that all of the y values in that open interval are smaller than the y value we have. An open interval means it needs to be on both sides. So if c is in an open interval, you're always going to be able to find points to the left and points to the right. So that is pretty key. Our definitions for our minimums are basically the same. There's only one thing changed, which is that f of x has to be greater than or equal to. So this says f of c is the biggest for a maximum. For a minimum, it's the same definitions, except f of c is the smallest point, either for the whole function or in that little area in an open interval right around the point you're looking at. And so f of x has an absolute minimum at x equals c if f of x is greater than or equal to f of c for all c in the domain of f. And f of x has a, not an, relative, so absolute minimum, relative minimum at x equals c if f of x is greater than or equal to f of c for all c, sorry, I keep doing for all c, for all x in AB. Sorry, not for all c, these should all be x's. In case you're wondering why I made this mistake, I actually recorded this video earlier and it was quite much better, but unfortunately I did it with no sound. So this is like take 2. So for all x element of the open interval AB, okay, such that C is in AB. So it doesn't actually matter what A and B are as long as C is in an open interval. And so x can be an element of any open interval around AB. Okay, so as long as there is some open interval AB. Okay, so the key thing here is because we need to be able to draw an open interval, if we're talking about a function that's defined on a closed interval, as we saw in our picture, endpoints for f of x defined on a closed interval AB can be absolute extrema, and we use the word extrema to talk about maximums and minimums. They're extreme points, but not relative extrema. So the endpoints can be absolute but not relative. So now we're going to take a look specifically at relative extrema. So relative extrema, and we'll go back and look at absolute extrema afterwards. So relative extrema, or local maximum and minimum. And I will probably be using the word local more likely just because that's what I used when I learned calculus many ages ago. So we have a C. If we have a local extremum, what we'll notice is that we're going from increasing function to a decreasing function here. Here, right at that extremum, we have f prime of C equals 0. Okay. Another thing that we could possibly have happen at a local extremum, let's look at an absolute value style function at C. We notice here that we are not differentiable because we have a sharp corner. So f prime at C here does not exist. And so if f prime at C equals 0 or does not exist, then f has what we call a critical point at x equals C. So a critical point could be a local extremum. It could be a local maximum, it could be a local minimum. We'll talk a little bit later, it doesn't necessarily have to be, but it could be. And Fermat's theorem says that you can't, at a local extremum, you can't have a derivative other than 0. So if f has a local max or min, an extrema, at C, and if f prime of C exists, then f prime at C equals 0. Okay? So if f prime of C is not equal to 0 at a point, then either it doesn't exist or there's not a local maximum or minimum at that point. So critical points, okay, and as we said, critical points were where f prime of C equals 0 or f prime of C doesn't exist, could be maximums or minimums, a relative max or min, or an absolute, potentially an absolute maximum or minimum, depending on what the rest of the function does. But they do not have to be. So they're not required, but do not have to be. So a critical point is not necessarily going to be a max or a min. So let's look at an example where we have a critical point that's neither a max nor a min. So if we look at y equals x cubed, we have critical points. Let's calculate those algebraically. Okay, y prime is equal to 3x squared. Our critical points are going to happen where y prime is equal to 0. So we have, or it doesn't exist. 3x squared exists everywhere, so we have 0 is 3x squared. So x is equal to 0. So we have a critical point at x equals 0. But if we go and look at the graph of y equals x cubed, we can see y equals x cubed actually doesn't have any maxima or minima at all. Let's make that a little cleaner there. Okay, so y equals x cubed doesn't have a highest point, so it doesn't have an absolute max, it doesn't have a lowest point, and it doesn't have any relative maxima or minima either. So what it does have is it does have a horizontal tangent. So the tangent line, because our derivative is equal to 0 at x equals 0, so that means we have a horizontal tangent line at x equals 0. But it's not a relative max or min. Okay, it's just a horizontal tangent line, and that can happen. So not all critical points are going to be maxima or minima. But if you have a relative max or min, it is going to occur at a critical point. Okay, so let's look at a couple, find the critical points. We're just going to calculate them. We're not going to try to determine what their nature is. That's actually going to happen in the next lesson. We're going to look at how to figure out whether it's a maximum or a min if you find a critical point. So if we have y equals x cubed minus 2x squared plus 5x minus 7, y prime is 3x squared minus 4x plus 5. We're going to try to find where it's equal to 0 to find our critical points because it's a polynomial, so there are no points where it doesn't exist. So 0 equals 3x squared minus 4x plus 5. I plug it into the quadratic formula because I can't factor that. So we have 4 plus or minus the square root of 16 minus 4 times 3 times 5 all over 2 times 3, which is 6. And we notice that 16 minus 60 is going to be negative. So x does not exist, or there are no real solutions. So therefore, there are no critical points. For our cubic, y equals x cubed minus 2x squared plus 5x minus 7. And it's kind of interesting to take a look at polynomials. So because this is a quadratic, it's possible that it doesn't have any roots. So we can have no critical points in a cubic graph. However, a quadratic has to have a maximum or minimum. So if you take the derivative of a quadratic, it's a linear function. And all linear functions have to have an x-intercept. So there has to be a point at which it's equal to 0. Kind of cool if you look at the higher degree functions, if that's something you're interested in. So here for b, we have y equals x to the negative 1/3 plus 2x. Let's find our critical points. So first thing is y prime is equal to negative 1/3 x to the negative 4/3 plus 2. So we're going to plug in 0 because that's where our critical points are going to be. So we have negative 1/3 x to the negative 4/3 plus 2. Okay, we are also going to be looking at where this derivative doesn't exist. So the thing is, we have a negative fraction. We have a negative point right here. So we may want to think about what's happening here. So we have negative 2 is negative 1 over 3 times the cube root of x to the 4th. Okay, so when x equals 0, we are going to have a big problem. So if we look back at our original function, it looks like because we have a negative, we're not allowed to have the cube root of x. That's going to be 0 as well. We're going to have problems when x equals 0 there. It's not necessarily going to be a local max or min, but we do need to point out that we should check. So it's going to be either a critical point or an asymptote at x equals 0. So it's something we're going to need to look into if we're going to be drawing the graph of this function. So continuing to solve for points, assuming now that x to the 4th is not equal to 0, we can multiply both sides by negative 3. So we get 6 equals 1 over the cube root of x to the 4th. We get x to the 4th, cube root of x to the 4th is 1 over 6. Multiply by 1, divide by the other. So x to the 4th is 1 over 216 if we cube both sides. And x equals plus or minus the 4th root of 1 over 216. Remember, when you're taking even roots, you need to look at both the positive and negative. So these are also critical points that we're going to need to investigate. Subveiling is suffering. Critical points that we're going to need to investigate. Okay, so I know a lot of you were saying, wow, Miss Eaton, This lecture has gone on for nearly 20 minutes and you haven't mentioned any trigonometric functions. Well, never fear. We actually have 3 seconds left. Here's some trig. So we're going to find the critical points for f of x equals sine x plus pi over 2. So if you recall, trigonometric functions are periodic. So if we think about just without putting in, this is a regular sine function with a bit of a phase shift. So if we think about a trigonometric function, just y equals sine of x, think about the fact that we are going to have many local extrema. Let's try to solve this one. So we have f prime of x equals cosine x plus pi over 2 times 1. And that 1 is coming from the chain rule. So we're differentiating. Sine goes to cosine. Inner derivative is just 1. So we get 0 is cosine of x plus pi over 2. Okay, so where is x plus pi over 2? We know that cosine of pi over 2, cosine x equals 0, for x equal pi over 2, 3 pi over 2, etc. So cosine of x plus pi over 2, we just have to back it up by pi over 2. So that's going to be x equals pi over 2 minus pi over 2, which is 0, pi, 2 pi, etc. And it's also going to include negative pi, negative 2 pi, and all of those as well. So we can state our solution. So x equals pi k, k element of z. That is the worst set I've possibly ever drawn. Let's try that again. Of z. So k is any integer. Are critical points of f of x. And so these are going to be, they're occurring every pi, and so that's going to be all of your maxima and your minima, because those are the points where cosine x of pi over 2 plus pi over 2 equals 0. Okay, so let's look at a few drawings and think about local maxima and minima. We've looked at how to find local maximums and minimums for a variety of functions, or at least how to locate those critical points. So now we're going to take a look at absolute maxima and minima a little bit and think about how we can maybe find those. So if we can, we're going to, the reason we do the local maximum and minima first is because we are going to use that for calculating our absolute maximums and minimums. So if we have y equals sine x that we were looking at last time, okay, we have our lovely graph here. And so this is our pi over 2. This one happens at 3 pi over 2. This one happens at 5 pi over 2. As we know, because we're all awesome at trig. This is 7 pi over 2. Okay, so y equals psi x has infinite local maxima and minima because it's periodic. So this is going to continue doing this, and it's going to keep, even in this short bit that we've drawn, we have 2 maxima and 2 minima, and it's going to keep happening. Okay, so there are infinite little local maxima and minima depending on how far we can keep drawing out the function. We can keep finding maximums and minimums. So absolute max, the absolute maximum value of this function is 1, and it happens, there are infinitely many times it hits that absolute maximum. Infinitely many times, and the absolute minimum is -1, and that also hits that absolute infinitely many times. So an absolute minimum is not necessarily unique. It just has to be the highest value. Okay, so let's look at y equals x squared, which is the main place that you've experienced maxima and minima up until this point is with quadratics. So we have here a very bad drawing of y equals x squared. we can see that there are no maximums of local or absolute variety, and x equals 0 is a local and absolute minimum. So it's a minimum for its little area, open interval, and it's also the lowest value of the entire function. So you weren't exactly wrong when you were just calling that the minimum, because it actually meets both definitions. So if we have y equals x cubed that we took a look at before, we start down here, we go up, we kind of get a horizontal tangent for a sec, and then we keep going up. This one has no maximums, because you can keep going any y value you reach, you can find a higher one, and no minimums, because any y value you reach, you can find a lower one. It just kind of keeps going on infinitely. So let's look now at a function that's defined, and this is where things get interesting when you're talking about absolute maxima and minima. Let's look at a function that is defined on a closed interval. So we have 3x to the fourth minus 16x cubed plus 18x squared. And we're going to define it only on the closed interval between -1 and 4. So this function looks something like this. So we have an a, point A up here. This is our -1. And go out to +4. So it kind of comes down. We definitely have a solution. Multiplicity 2 here at 0. Come back up. And we could actually calculate these if we felt like solving a cubic, but we're not going to bother. Then we go up, and then we hit something here at 4. Okay, so let's call this A, B, C, and D. Okay, and we'll call this, let's actually make this a little bit more like that. So this is E, just to make it clearer that E is lower than A. So A is an absolute maximum. B is a local minimum. C is a local maximum, but not an absolute max because A is higher. And D is a local and absolute minimum, because it is the lowest point in its area, but it is also the lowest point on this entire closed interval. So we notice absolute maximums and minimums are not occurring at just any old point. They can occur where it's already the highest or lowest point in the area, so at a local max or a min, and they can occur at the end points, because the end point might be starting higher or lower. So from this, we get the extreme value theorem, which I'm not going to derive, but you can check your textbook if you'd like to see it derived. So the extreme value theorem. So if f is continuous on a closed interval. So it's very important that we're talking about a closed interval. A comma B. Then there exists C and D that are in AB, where f of C is an absolute minimum value, and f of D is an absolute maximum. So what this is saying is if you are on a closed interval, so that means it can't be continuing infinitely in either direction, and it can't be an open interval, so it can't kind of keep getting closer and closer but not quite get there. It has to have two endpoints. Then there has to be a highest value and there has to be a lowest value. Doesn't have to be unique, it could be repeated, but there has to be that value. So just a note, if f is not continuous or not defined on a closed interval. So those two things are required. It has to be continuous and defined on a closed interval. Okay. There may not be absolute extrema. Okay, so if you're on an open interval, there might not be absolute extrema, and if you are on, if the function is not continuous, there may not be extrema. So you have to have all of those things be true. Okay. So an example here, okay, if we have part of a function that's defined on an open interval, so if you have 4 and 2, and we have y equals x squared that's defined from here, so y equals x squared for x that are between 0 and 2, but on an open interval, there are no maxima or minima. This also doesn't say anything about whether, the extreme value theorem doesn't say anything about local maxima or minima and whether they exist. It's only talking about those absolute, the highest value on that whole closed interval and the lowest value on that closed interval. There are also, now that we understand when we can be sure of finding a relative and absolute maximum or minimum, there's only a limited number of places that we are going to be able to be found. Okay, so absolute maxima and minima are found at, number 1, they could be found at critical points. F prime of x equals 0. And this is where you're also going to find local maxima or minima. They're not necessarily all going to be local maxima or minima, but this is where you would find them. The other place that could be an absolute maximum or minimum is endpoints for functions defined on closed intervals. And these endpoints cannot be local maxima or minima, as we saw in a couple of the graphs. Okay. So to find, first thing you do is, number 1, find all critical points. Okay. Then find f of c for all c is a critical point. Find all critical points c, and then find f of c. Number 2, for f defined on a, b, find f of a, f of b. And let's add that this is continuous, otherwise our extreme value theorem doesn't apply. Okay? Okay. The largest of these is the absolute max, and the smallest of these is the absolute min for f of x continuous on the closed interval from a to b. So if you have a function defined on a closed interval, and this can be really useful when you're doing word problems, because often the functions you define for word problems will end up being defined on a closed interval. You find the relative maxima and minima by finding the critical points and determining if they're maxima or minima. You find the endpoints, and you find the value, the y values of the endpoints. The biggest y value you get is the maximum. The smallest y value you get is the minimum, using the extreme value theorem. In the next lesson, we're going to look at how we determine whether we have a relative maximum and minimum. So the next lesson we'll look at using the first derivative to determine whether you have a maximum or a minimum. The lesson after that, we'll look at how you can use the second derivative to determine whether it's a maximum or minimum, as well as looking at how the second derivative can tell you about what the graph looks like in a certain region.